So before we jump into what a log is, let's remind ourselves of the relationships that logs have with exponential equations. If I take an exponential equation like this, and I want to find the inverse of it, my first step would be to swap x and y, and then I would need to get y by itself. Well, up till now, we haven't actually learned any operation that would get y out of the exponent location. The operation that we would use would be to take the log. So we would switch this into log form, and we would get this. These are equivalent equations. And that gets y out of the exponent and allows us to find the inverse. So an exponential and a log equation are inverses of each other. So let's actually figure out what is a log and how do I evaluate it and how is it useful to me when I'm trying to solve equations. That's what we're going to spend the rest of the chapter looking at. So a log that looks like this, a log equation, we would read this as log base b of a is x. And it's just asking an equation. It's asking what exponent do you need to get from a base of b to get to a? And the answer would be what it equals, x. Or you could rethink to yourselves, b to the what equals a. So let's practice that a little bit on the next few problems here. We have log base 2 of 16. And all that's doing is asking a question. What exponent do I need to get from a base of 2 to get to 16? Or we might think 2 to the what gives me 16. And the answer is 2 to the 4th power gives me 16. For the next one, log base 8 of 512 simply means what exponent do I need to get from 8 to get to 512? And the 2's we're really familiar with, but I don't necessarily expect you to know all of the 8 powers. So your calculator would be very beneficial in this case. We of course know that 8 squared is 64, but 8 to the 3rd power gives me the 512 that we needed. So what exponent did we need to get from 8 to 512? We needed an exponent of 3. Log base 8 of 512 equals 3. Log base 5 of 125 simply means what exponent do I need to get from a base of 5 to get to 125? The answer is I need an exponent of 3. 5 to the 3rd gives me 125. They have a very close relationship with those exponential equations. What exponent do I need to get from a base of 4 to get to 16? Well, 4 squared gives me 16. So what exponent did I need? 2. Now our missing value might not always be at the end of an equation. It might be hidden throughout the equation. So we have what exponent do I need to get from a base of 2? And the number I'm trying to get to is my unknown. But the exponent that they're using is -1. So 2 to the -1, if you remember back from exponential equations, gives me 1/2. When we have a negative exponent, it crosses that fraction bar. Log base 10 of 1 over 1,000 simply says what exponent do I need to get from a base of 10 to get to 1/1000th? Well, we know it's got to be a negative because it goes to a fraction. And to get from 10 to 1,000, we need an exponent of 3. So what exponent did I need? -3. And that's kind of that same skill that you were practicing when you were doing exponential equations, finding that common base or what exponent would get me to a number that I need. In our last example on this page, we don't know the base, but we know we're trying to get to 81. And we know that we're going to use an exponent of 2. So what number could I square to get to 81? 9. The next part I want to show you is, we just practiced doing this by the location of where everything is in the logarithm. But sometimes when we're converting back and forth, it can be helpful to have another tool in our basket to help us convert from logarithm form to exponential or vice versa. And the tool that we can use there is called the loop. So you can draw a loop to kind of tell you the order that it would appear when it's in the other form. We always start our loop at the base. It always goes around the equal sign, usually counterclockwise if the log is on the left. Goes around the equal sign and heads to the number next to it. Now that tells me the order that it would appear in the other form. B to the x equals a. B to the x equals a. Or if you're switching from exponential to a log, same thing, goes around the equal sign and ends at the number next to it. Log base b, next thing my loop crosses is a, and it ends at x. Whether you do it this way or you do it just by knowing the base, what number I'm trying to get to, and the exponent, it does not matter to me. Let's take a look at, we have common and natural logs. Now, as humans, we typically find any way that we can shorten something, we will. For example, that's why we have contractions. Instead of saying do not do that, we can say don't do that. We even see in our daily lives, we shorten. Maybe when you're texting, you don't write the whole thing out, you abbreviate or you use letters to represent an entire phrase. That happens in math as well. For example, you know that if I put x, the number in front is understood to be a 1. It's the same thing. Even if we don't see it, we know that the 1 is there. We also know that if I have a square root, the index is 2, even though there's not a 2 written there. Well, the same thing is happening with logarithms. We have logarithms that are used a whole lot when we have applications, for example, in the sciences or in statistics and actuarial science. Logs that have a base of 10 and logs that have a base of what we call e are used quite frequently, so much so that they came up with kind of abbreviations for both of those. Whenever we have a log with base 10, we don't write the 10, we just write it with a missing base. So if you see a log that doesn't have a base, its base is 10. Same thing happens with what we call a natural log. Now, for a natural log, we have a log with a base of e, which we write as ln. E is actually just a constant, similar to how you would say pi is 3.14. E is a constant as well. You can find it on your calculator by pressing second and the division key, and you can find out that E's value is 2.718 blah blah blah. It stands for a number, the same way that if you got it to say pi, it would spit out the equivalent for pi. So E is a constant, not a variable. And when we have E as a base, we write it, instead of writing it as log base E, we write ln for natural log. So you might see that as we move through some of these examples. For this one, let's switch this equation into exponential form. And we can do that either with a loop or with just identifying what the pieces are. I'll draw a loop for all the problems, but if that's not how you remember it, that's okay with me. So if you use a loop, it would look like this for each of the problems. Either way, we have a base of 8. The exponent would be 3 because that's what it equals. And the number we're trying to get to is 512. So this is what it would look like as an exponential form. Next one, the base is 5. We're trying to get to 625, and we're going to use 4 as our exponent. Next one, we have an ln. That means the base is e. The exponent we're using is 42, and the number we're trying to get to is x. Here's that ln again. That's e. The number we're trying to get to is 18, and the exponent is x. So whether you follow the loop for your order or you know the different pieces and where they go, you still get an exponential form that looks like this. How about moving from exponential form into logarithm form? I'll still draw the loop for you if that's the way that you learn or the way that makes sense to you. We have log with a base of 11. Make sure you make your bases lower and smaller. The number it's trying to get to is 1,331, and we're going to use an exponent of 3 to get there. Next one, log with a base of 16. We're trying to get to 8, and the exponent we're going to use to get there is 2/3. Log with a base of e, remember we don't write log base e, we write ln of 30, that's the number we're trying to get to, equals the exponent of x. And for our last one, log with a base of e is written as ln. The number we're trying to get to is x, and the exponent is 3. So you should be comfortable with flipping both from logarithm to exponential form and logarithmic form or exponential form to logarithm form. The whole purpose of that is so that we are able to solve equations like this and the equations we'll see in our next standard. So equations that look like this, we would want to switch them into exponential form. So here's your loop if you use it, but our base is e. The exponent that we're going to use is 4/3, and the number we're trying to get to is x. And you can see that once we switch it to exponential form, all we need to do is type into our calculator. So 8 to the 4/3 gives me 16. Number 6. Our base is 16. The exponent is 3 to the 4th. And the number we're trying to get to is x. So 16 to the 3/4 just needs to be put into my calculator. And I get 8. So that was really easy when what we were looking for was the number we're trying to get to. But occasionally we're going to have to figure out the exponent. So we're going to switch to exponential form because we might not know off the top of our head what exponent would get us from 8 to 16. But switching it to exponential form gives us other options. Log base 8, the exponent is x, and it equals 16. Well, this now looks like an exponential equation that we did in our last skill. We can find a common base for 8 and 16. The common base for 8 and 16 would be 2. In fact, 8 is 2 to the 3rd power and 16 is 2 to the 4th power. So I can replace the 8 with 2 to the 3rd power and 16 with 2 to the 4th power. As we know from previous lessons, when the bases are the same, the exponents can be set equal. So 3x equals 4. Divide by 3 on both sides so that x equals 4/3. Number 8. The base is 27. The exponent is negative 1/3. And we're trying to get to x. Since we're looking for the number x, and all I have to do is type in as 27 to the negative 1/3 and change it to a fraction. X is equal to 1/3. So our base was 3. We're trying to get to 81 using what exponent? And you may already know this one off the top of your head, but you can also use common bases. 3 would be our common base, and 81 is 3 to the 4th. So the bases are the same. Our exponents are equal, meaning that x equals 4. Since the standard specifically says that we have to use a logarithm to solve an exponential or solve a logarithm using an exponential, we do want to see what it looks like in exponential form so that we know that you've made this connection. Here's our loop. So our base is 2, trying to get to x, and we have 1 over 16. Or sorry, base is 2, the exponent is x, trying to get to 1 over 16. Common bases would be another good place to start for this one. 2 would be a great common base, 2 to the x, and 1 over 16 is 2 to the negative 4. The bases are the same, so setting the exponents equal gives me my answer. X equals negative 4. For number 11, we can draw in our loop here. So the base is 1/3. I'm trying to get to 27 using an exponent of x. So a common base is going to be helpful here. Our common base is 3, and I have to switch both of them. I have to switch 1/3 to a base of 3 and 27 to a base of 3. 1/3 would be 3 to the negative 1, and 27 would be 3 to the 3rd. So I'll replace my 1/3 with 3 to the negative 1 times x, and 27 with 3 to the 3rd. The bases are now the same. I can set the exponents equal to each other. Negative x equals 3. Divide by negative 1 on both sides, and we get that x equals negative 3. Here's our base around the equals and at the number next to it. So the base is 5, exponent is 5, and we're trying to get to 3 minus x. So the first thing that we'll do is raise 5 to the 5th power, which gives us 3,125 equals 3 minus x. Now we'll subtract 3 from both sides and divide by negative 1. So x is equal to negative 3,122. For our last problem, our base of ln is e, our exponent is 8, and it equals 3x. Now, I know that we talked about your e being second and the division button, but we actually have another place that we can use when we have to raise e to a power. It's right here on the natural log button. The natural log has its own button on your calculator. So if you press second and ln, which is located next to the 4, you get e to the exponent. Second and division will work the same. You'll just have to make sure you raise it to an exponent on your own. But e to the 8th equals 2,980.6. 0.958, and that equals 3x. We need to divide by 3. Notice how I kept this long number in my calculator. I didn't want to round it until the very end. We just round to keep track of that number on our paper. So dividing by 3 on both sides gives me 993.653. We'll round it to the nearest thousandth.